let me also welcome Matteo Novaga, who's the first speaker from Pizza, and he will be talking about curvature flows with obstacles. Yeah?
Okay, thank you. Okay, so thanks for the invitation here. Very nice place to stay. And so I will talk about, essentially my talk will be a little bit more abstract than other talks, so I hope not too much. And I want to present some methods, essentially to define and possibly compute solutions for geometric problems, in general geometric evolution equation, also in presence of obstacles. And in particular, we make two examples. So the main one, which is better understood, is mean curvature flow, and maybe I will say something also on higher order evolutions. So in particular, I'm looking now to evolutions which are gradient flow of some energy. So the typical case is one has some obstacles, which are, of course, obstacles, let's say for now they are fixed and smooth, but maybe later they can also move in case. And one looks at an interface, sigma t, where t is time, which has to be contained, so essentially cannot enter the obstacles. So if there is a constraint of this type, sigma t is contained in a subset, which is a complementary set of the obstacles, and sigma t with flow following the gradient flow for some geometric functional. The geometric functional is typically some energy of sigma, which will be, well, in general, will be maybe a combination of different geometric quantities. For example, there can be a perimeter integrate over sigma, a constant which gives you a surface area term, plus maybe, for example, typically you can have in applications to physics or to biology also higher order terms. Let's say the simplest one would be just the curvature square. Well, typically as a convention I indicate by h the sum of the principal curvature and minus 1 times the mean curvature. H is the mean curvature, let's say, up to a constant. And then of course you could add here, okay, here sometimes it's h minus some constant, then you could have also higher order terms, but let's say that's a typical example which I'm interested in. And so in particular there are two examples I will discuss more in detail. Two examples are, so sigma will flow by the gradient flow of that energy. When you say gradient flow, you have to specify essentially which norm you use. So gradient flow, I mean L2 gradient flow, in the sense that if you write the energy as a graph, you take the L2, the normal L2 gradient flow. So okay, so the typical example are the energy, which is the area of sigma. This will produce the mean curvature flow, which where V denotes, V here denotes the normal velocity. The scalar normal velocity point is, it depends, now when I use this convention I think H as a scalar, which is positive on convex, and V is a normal velocity, which is a scalar, and the direction is inward, but there is only a matter of convention for the sign. And another example, typical example, but more difficult somehow, is this one, which produces now with this convention of normal inside, I think there is a minus here, minus Laplacian of H minus A square H plus H cube. And this is, so this is a mean curvature flow, and this is a Willmore flow or elastic flow, where the Laplacian is the Laplacian on the surface of the mean curvature, and this A square is the total second fundamental force. So A square here is the sum of Ki square. Okay. In particular for curves, this is also known as elastic flow, and it's been studied quite a bit. Okay, so now as one can see with simple examples, in the relevant, maybe in the more relevant the physical dimension, which is 3, both flows generate singularities, and in dimension 2 much less. So dimension 2 is a little bit specific because these flows are more regular. But let's say in dimension 3, for example, or higher, both flows develop singularities. It's very easy to give examples. So, for example, for mean curvature flows, there is this well-known examples of a bone-shaped, dumbbell-shaped thing which will shrink, and when it shrinks, here the mean curvature will blow up. And also, there is a more complicated example. Now, I will not give a picture of that. A more complicated example for the Wilmot flow. But in any, because the Wilmot flow is more regular, so you have to pick up more complicated examples of singularities. But in general, these flows, there are singularities in finite time. So this is a little bit of an historical sort of a view, in the sense that what has been done and why, even without the presence of obstacles. Then I will at some point say how to include these obstacles. So once you have singularities, now the natural questions are essentially, there are a few natural questions are, well, how to define a solution which is which goes beyond the singularities. So definition of global weak solution. Global weak solution. Well, of course, there is an issue, sort of basic, which one say it's simple issue, but still there is an issue, at least to show that you don't have instantaneous formation of singularities, and that's another issue. So local regular solutions, smooth solutions, and then there is the issue of analysis of singularities to understand how the singularities are done by typically by some blow up methods. And in particular, I will now concentrate on one method only. There are here several, on the first point, how to define a notion of solution which goes beyond the singularities, and maybe I'll try to give some regularity information on the solution, and we'll observe that essentially this definition I will give easily is adapted easily to the presence of obstacle, so it will be natural. So okay, so I will concentrate on the notion of weak solution, and of course when you have a notion of weak solution, you would also like to have a way to compute it, maybe if you have to do a computer simulation in a sort of efficient way, and not every weak solution is has the same difficulty in computation, so that's also an issue which can be interesting if you want to compute the solution. Okay, so concerning the weak solution, I will describe a method which by now is well known and has been introduced in the early 90s by Almgren, Taylor, and Wong, and simultaneously by Lukausen and Sturzenegger, which is essentially to just do the gradient. So the idea is to do a Newton method on this energy. So in some senses to discretize time and minimize the energy with a penalty term, and then sort of pass to the limit in the discretization parameter. So there is this implicit scheme, variational scheme, which the way I write it can be very general, does not depend very much on the energy, but then of course if you have to prove something on the solution you get, then it depends very much on which energy you take. So the implicit variational scheme due to Almgren and Taylor, Lukausen, and Sturzenegger is the following. You fix a parameter tau, which is a small parameter, we just discretize time, and then you start from your initial set 0, which is your initial set, where I define E0 to be the set whose boundary is my sigma. So I start from the initial hypersurface, I choose as a set the inside of the hypersurface, typically a bounded set. And then I minimize, I define an iteration which is the following, En plus 1, which is a set at step n plus 1, which is the minimum of the energy. So this will be the argmin of the energy, now, which is my energy up there. Now I define if you want, the energy of the boundary. plus a penalty term. It's like for Newton method, you don't want to go far from the previous step. And the penalty term is something like that. You can write in two ways. One way is this one. You can either write with the symmetric difference, or let's say you can write even in this way, or E, the distance from the previous one divided by the small parameter tau, when this distance is a sign is a sign distance function. You want to distinguish the inside from the outside. So the distance from a set E will be the distance from the boundary of E if x is, for example, x is outside, and minus the distance if you are inside. So it's a function which essentially is like that. And when you minimize that, essentially you see that the Euler-Lagrange equation, which you get, is that the gradient, so when you minimize the scheme, you get something like the gradient of E plus on now it's a little bit formal, but just to say why. So I just want to motivate with one word why you choose this penalty term and not some other penalty term. I mean, it comes from the first variation, basically, if you want, because you get something like this. And so essentially it's a gradient of the functional, and this a little bit formal, of course, this, and this is just the distance after a time tau divided by tau, so the effect will be a discretization of the velocity. So in some sense it's coherent with velocity equal minus gradient of the functional. That's the motivation for this. If you don't put the distance inside, you get a different evolution. Usually, often it does not even move. Okay, so now how do you, now you are just creating an iteration.
Okay, what is the connection between the nth iteration and tau?
Okay, for the moment tau is just appears as a parameter inside here, but now you have to pass to the limit, and when you pass to the limit you define an approximate solution E tau of t by just patching together all the En you obtain by iteration standard, so it's something like E of n over tau, which means just be E0 for the first tau time, then E1 for the first tau time, and then this will be, it will jump at each tau, and then I define E of t to be now the limit. Typically this limit will be taken in L1, so in a weak sense, L1 of characteristic function, sort of weak sense. So it's quite a weak solution, this one here. But it has at least one little advantage by construction, that the energy decreases on the solution, because in fact it will decrease at each step. The energy goes down. So at least you define a solution which is very weak, but the energy of, now I put the bound, will be decreasing in time, and the solution will be defined for all time. Of course, now the questions are the natural questions, which maybe I will discuss what is known for mean curvature flow. Of course, the regularity, uniqueness, generally not unique, and also in which sense the equation is satisfied. The equation, let's say. Because now this variational solution, okay, formally you sort to expect to satisfy the equation, but since the object is quite weak, you have to understand in which sense the equation, in fact, will be effectively satisfied. So let me, okay, so the definition is this. Just a remark that it's very simple to include obstacle in this formulation, because you include obstacle at this level, and from the point of view of minimization, the presence of obstacle is something which will be typically you have obstacle inside and obstacle outside, so it will be some constraint like that which behaves very well for this type of minimization problems. So it's not to include obstacles in the scheme this formally to get a weak solution is something you can do easily here. So that's an advantage. Okay, so let's see now what.
Can I ask you a question? When you include obstacles, how do you count the perimeter?
Sorry?
When you include obstacles, how do you count perimeter?
Now if I include obstacle like that, I count the energy on the obstacle too, which means in particular, for example, that if I touch the obstacle, the perimeter will be counted. And of course you can, but you can also do something where you have to change the energy differently. You have to change the energy here. For example, you have to put the perimeter inside your set. You can do this too. You have to be a little bit more careful. But what I'm presenting now is that you count, for example, for higher order flows, it will not be convenient to touch the obstacle, because when you touch, if the obstacle is irregular, you will pay a lot. So now I'm counting all the energy. So it's a simpler situation, maybe. Okay, so the perimeter is all the perimeter. So for the mean curvature flow, which was the subject of the original paper by Alme Wong, one can prove, in fact, that there is at least a continuity in time, which one expects very well, and then it's not difficult. So for the mean curvature flow, so the energy again of sigma is just the integral of 1 of sigma, then it's easy to show that this is continuous, in fact is Holder continuous with exponent 1/2, but in any case is continuous in the L1, which essentially, it's a weak continuity. It essentially says that you don't jump. And the fact that you don't jump here, for the mean curvature flow, is relatively easy to show for the following reasons. The mean curvature flow, it's a second order flow, satisfies the comparison principle. And so this is a very weak continuity. It says that I don't gain a big portion of space, and it's enough to just put little balls, and to say that the little balls will cannot be eaten instantaneously by comparison principle. They will evolve like balls very explicitly. Since you cannot eat balls from this type of property, comparison principle, you get continuity, okay? So at least you have some minimal regularity, and then of course you get that here the boundary of E of t that was proved is contained in the zero. They showed they compare the solution with other solutions, and the well-known solution is the viscosity solution, and they show that in fact this is contained in the viscosity solution, which I will not describe now. It's a solution obtained by the level set method. And also there is an easy way. It's easy to implement this scheme for mean curvature flow, because as a remark, you can reformulate this minimum problem, which is a geometric minimum problem, as a relatively simple convex problem to study. So from the point of view of computation of the solution, now I want to, the minimum problem I wrote, 1 over tau. This was the set before. So this minimum problem can be reformulated in the following way. I want to write for a function u this minimum problem at each level set. So sort of want to write a problem for functions, not for sets, instead which correspond to this one for each level set. So I want to integrate on level sets this problem, this co-area type formulation. If I do this, this becomes quite nice, because it becomes just the minimum of the total variation plus u minus d en square tau. And I think you can even put a square here. I'm not sure, completely sure, but this is analogous. This is exactly the same problem. So, and now you recover your set En plus 1 as the minimum, the zero level set of the minimum. And now this is easier because it's a convex problem. There are a few methods to compute. It's a way to compute this one effect. Okay, so it's in some sense it's also easy to do simulations once you formulate in this way. Okay, everything which I wrote here can be adapted to the case of obstacles. So I will not, in fact, talk too much, but everything which I said, in particular the existence of a solution, some continuity in time, and also some coincidence with some weak solution, can be extended without any change to the presence of obstacle. But now everything works with... now let me comment on another difficulty, which is when you have obstacles. So if you have obstacles, with obstacles, so essentially with obstacles it's not so easy now to have, okay, it's relatively straightforward to have a weak solution for a long time, but it's not so easy to have a regular short time solution in the geometric case. So the idea was, our idea at some point was to try to use this method to construct also a smooth solution for short time. So is it, in particular, the question which you can formulate even without obstacles is it true that if the initial set is 0 is smooth, then E of t is also smooth for short times? In the particular case of mean curvature flow, you can do this result in a different way. Typically, you can parameterize the surface, or you can write the evolution as a graph over a surface, and then you end up with a parabolic problem, which is well posed and everything, and you have short time existence. So it was a little less clear how to extend this to... we wanted to see to the case of obstacles, so we wanted to see if it's possible to work directly with this solution and to show the regularity of the solution for short times. Okay, this we have only, so without using a different method, without parameterizing and having in another way a regular solution, just to look at that variational solution, and because this has advantages, it's quite flexible, this method. And if you are able to show regularity directly by using the variational method, maybe you can show regularity also for more general evolution equations. For example, other equations which are difficult to study are degenerate anisotropic equations, where really the PDE becomes a little bit bad, but this method works the same. So our idea was, is it possible to study? And so here there is we can do only in dimension 2. Obstacle or non-obstacle, again, is the same for this type of evolution. And essentially what you get is E of t, if the obstacles are smooth, at least, E of t is C11, which is a more or less optimal regularity you can expect, because when you have obstacles, of course, and even in the stationary case, you might expect that the second, the curvature will jump. So C11 is sort of optimal regularity. So E of t is C11 for short times. But in dimension n greater than 2, we had to use a completely different, we had to use a different approach to establish the same result. And maybe I will describe briefly the other approach we had to use, but we don't know how to prove this directly. And because essentially there is a problem, which I think is maybe the only significant problem for this type of scheme for mean curvature flow. It's a regularity issue, and it's the following. Is it true that if I want to show that the solution is C11, is regular, essentially one way to prove it is that the solution will satisfy some ball condition inside and outside. So I can put a ball inside and a ball outside, and I have to control the radius of these balls, and this will be a way to control the C11 regularity of my minimizer. And so the regularity issue is the following, and we don't know, so it's like a problem just formulated in this case. If it's true that if E0 satisfies an R ball condition, where by R ball condition I mean that at each point I can put two tangent balls, one outside, one inside with R, then E1, so a minimizer of my problem up there, as I do one step, how much do I lose in the radius of my ball condition? So I want to show that, I think it's true, but I don't know how to show it, that E1 satisfies let's put here R0 and R1 ball condition, and since I want to iterate, I have to show that R1 is greater than R0 minus C tau. C can depend from R0 and I don't know. But so I think this one is maybe an interesting problem, because if you can solve this regularity issue, it's a little bit like a problem of regularity for prescribed curvature problems like this, but in a slightly unusual for me formulation. And so if you can show this, then you can adapt the method and show short-time existence and of C11 solution for obstacle, but probably also for very degenerate like crystalline evolutions. So it can be, so just to state. So the problem is to control this radius. Okay. Now, in fact, the way we found, which it's different, it's a bit different, in fact, to show that, in fact, in the particular case, specific case of mean curvature flow, you have, in fact, regular solutions. It's the following. In fact, you can essentially what you do is the following. You can regularize obstacles by transforming the obstacle in a forcing term for the evolution. So essentially, if I let's say approximate the obstacles with soft obstacles, and in fact I look not to the mean curvature flow but to the mean curvature flow plus a forcing term G epsilon, where typically G epsilon will approximate as epsilon go to 0, something like here you have a big constant, here you have something like minus a big constant. So it's a function, it's a forcing term which push you out of the obstacle. I put plus and minus because as this one is inside, this one is outside, it comes from the sign convention. And so in a way, if C is big enough compared to the curvature of the obstacle, the obstacle becomes super and sub solution for this forced mean curvature flow. And so the mean curvature flow with this forcing term will be equal, thanks to the comparison principle, so it's related to the mean curvature flow, to the parabolic, will be equal to the flow with obstacle. And now here you have an equation which is somehow more regular, and you can hope to have to apply, let's say, directly PDE techniques, because now so one approach is the following. You first of all you regularize the obstacle with the forcing term. Second, you write locally this equation as a graph, locally as a graph on the initial datum. So locally, this equation becomes the equation for graphs, which is the mean curvature flow is like that. You have this term here. This term is due to the fact that you are not moving vertically, but you move sort of in the direction of the normal. Then you have the mean curvature, h. This is h. And then you have a forcing term, which now depends also on u, because G depends on x, but when you write as a graph depends also on u. And here you can do the usual estimates, which are again typically based on comparison principle, because it's a second order. And here so this is again like it's a local formulation of that, local formulation of this one. And here you can get a bound on the gradient. You have to be a little bit careful for two reasons in doing this, because first of all is a local formulation. You have to put some test function somewhere. And then second, you have this term, which is, now I'm slightly cheating. This estimate do not go for any, you have to use the structure a little bit to the forcing term. But essentially, you differentiate and you apply maximum principle, and you obtain a bound of this form, and also of this form. And then you show that you epsilon, and also on the existence time. And so show you that u epsilon will go to some u Lipschitz, and the u Lipschitz will be a Lipschitz solution, in fact a variational solution to the parabolic obstacle problem. Then you can apply the regularity theory, which is well developed for the parabolic obstacle problem, and you derive sort of easily that that you have C11, if the obstacle is smooth, you have C11 regularity in space. Somehow you're using different things now. You're using the regularity theory for the obstacle problem, you are using this approximation of the obstacles with a regular Foxing term. In a way, it's a way more complicated than not try to do the estimate directly on the variational, because we are not able to do that. So that's, but in any case, as a result, you have this regularity. I know a little bit less about the regularity of the free boundary of the contact set of the C11 solution. Here I'm not an expert of that part, so it's here. But you can construct for short time a C11 solution for the mean curvature flow. Now I wanted now to say what you can do for the Wilmore energy. Yeah.
You said that for n equals to 2, you could do that
Directly.
locally.
Yeah.
But why is it that you cannot do it for higher dimension?
Now, for n equal to 2, we can do just by looking at the variation, at the minimizer of that variational problem, which the variational problem I wrote with the distance divided by 2. Because in dimension 2, the Euler-Lagrange equation, this Euler-Lagrange equation here has a curvature in. When E is a perimeter, the gradient is a curvature. And so somehow, from the Euler-Lagrange equation, from being a minimizer, you already control the curvature. You have some control directly on the curvature. While in higher dimension, to control the mean curvature is not exactly like to control the full second fundamental form. It's like to control the Laplacian or the full Hessian. And the estimate you get works. You cannot win. So it's probably a technical issue here, I don't know. But using the Euler-Lagrange equation, for example, that's one way to say it. You have much more information in two dimension, because basically the mean curvature is a full curvature. So, and in higher dimension it's less.
To me, it's like you get the mean curvature equation locally when you have the obstacle in the direction when the obstacle is a graph.
Exactly.
And then outside that, you have the classical problem, flow by mean curvature.
Yes. In fact, the problem is close to the obstacle somehow. But no. But even without obstacles, no obstacles, everything is very smooth. If you want to do this estimate directly, we don't know how to do at least this estimate directly. Because the way it's done, usually, the way you do short time existence for mean curvature flow, it's a little bit, probably, how do you do normally? You linearize the equation, you solve, and you do a sort of fixed point argument, and sort of embedded in this argument, there is also this estimate of the second fundamental form, but it's difficult to make it explicit. The classical proof of short time existence and regularity is by linearization. While here I would like to have directly an estimate on a nonlinear, which maybe it did not just work enough to get. I think it should be true. So now, just since in the last 10 minutes, I want to comment what about the Wilmore. The Wilmore, so the energy of sigma is now the integral, let's say, of h squared, and this gives to the Wilmore flow. So, but basically nothing is done here in this respect, but I think that this method could be useful to generate weak solutions also for this flow. It's more difficult to do. Typically, weak solutions for the Wilmore flow are done differently. In simulations, are rather done by phase field approximation, like Caniglia approximation. So in any case, I don't know about work using this variational scheme, which you can implement. First of all, a couple of comments. Here you don't have the maximum principle anymore. And so here, no maximum principle has some consequence. In particular, you have to understand which is the solution you are looking for here. Because even in two dimension, which where the flow is relatively well studied, when you have an evolution, you might have the presence of singularities without that any geometric quantity blows up. And the singularity is just due to the fact that two parts of the same object come together and touch each other. For example, here, They touch in a way that the curvature, you see, here you are in two dimensions, nothing blows up, and you can have in any dimension. So now you have to decide in your evolution, by this elastic flow, Wilmore flow, how do you want to proceed? Because here, usually people, the majority of the works here are done by parametrizing the surface. If you parameterize the surface, and then you solve the PDE by standard method. If you do this, then here you decide to proceed in this way, because you parameterize, you cross. Which might, maybe in some model, in some case, maybe you don't want this type of crossing. And on the other hand, you could decide to split. But you see, if you split here and sort to regularize, for example, by approximating the set from inside, when you do this, the energy will jump up a lot. So this solution will not be the solution which you reconstruct by this variational method, which forces the energy to go down step by step. So in particular, you do that, the energy jumps up. This will not be reconstructed by the method unless you force something strange. I don't know how to do it. Okay. So what this method will rather do is to keep track of this connection. Somehow it's like if the membrane cannot be, this membrane cannot be broken. So something like that, there will be sort of a filament, remembering that there is something here and here, and maybe after some time this can be again something like that. So that will be the type of solution which will be reconstructed by this method, if one can. And here you see already there is a difficulty, and the difficulty is the fact that this is not really a set, in the sense that it's a set plus this filament. So what I want to say is that here you have to define the domain of your energy. And the domain of your energy has been studied, but it is a little bit complicated because it's sets completed by this filament, and usually to properly define you have to enter some language like variables, and becomes a little bit more complicated to implement the scheme, just to start with. Because you have essentially to remember these ghost lines, at least until they become again thick. So already the formulation is, first of all, not so straightforward. So I'm now, in fact, presenting the problems more than the results. Maybe you see. Second problem related to this is that, in fact, even when you want to compute, you can just do the computation. Well, this by level set is not as nice as for the mean curvature flow, for which you end up with a convex and relatively easy to compute functional. Because here the level set formulation, so if you write this on level sets of a function, for example, to compute effectively, you end up with a functional which is more complicated, which is something like, you can of course regularize the mean curvature of the level set, which reads like that, square, and then you have this du, and this is less nice than the other one. For example, plus, of course, this is a convex always, plus this penalty term. This is good, this is less good. Then you can find ways, of course, to probably to regularize this one. You could put here, for example, a z, and then force z to be but still. So this would be a better formulation, and otherwise, but still is not as nice as before to compute directly. And finally, just as a final remark, much less is known also about the regularity. Now, in fact, it's mainly open questions for the Wilmore. Much less is known for the regularity theory for the Wilmore energy in presence of obstacle, even in the stationary case. For example, the regularity. This is something which maybe would be interesting to understand. Regularity. If you have obstacles, smooth obstacles, it would be interesting to understand at least in the stationary situation. So let's say for a moment we forget about time, and you want to just minimize the integral of h squared with this on the boundary of E with omega 1 contained in E. This is E. These are the obstacles contained in omega 2. So it's a geometric, this one is a geometric obstacle problem. You just, instead of minimizing the perimeter, like for minimal surface, you minimize the Wilmore energy. And the question is, what is the regularity which you expect here, and do you get, as you would expect, C11 regularity for partial E? I don't know much. I don't think this there is much about this. But what I found, in fact, looking a little bit at the literature for this type of problem, is the following. There is some work, relatively old work by Caffarelli and Friedman, studying the linearized situation. So linearized situation, which means that you take the simplest linear. So the gradient is a first order problem, this one, not a second order problem. And so the simplest problem you could sort of use as a model to see what is the regularity you could expect is this one here, the B Laplace of u equals 0, with some obstacle which is smooth, and u, let's say, greater than f. Then, of course, you can have some other obstacle, you don't care. And so this would be the linear, a simple linear analog of that. And of course, there is also, which can be treated similarly, let's say, the parabolic analog, linear, which would be some sort of, so the question would be to analyze the regularity of this type of solutions, which are, and then you could expect that the same you could maybe have in the nonlinear geometric case. So for this case, in fact, for this case, and also for this case, which I will not comment because the results are similar, the result you get, in fact, is that the function u, this is an old result by Caffarelli and Friedman. In fact, the function u is C11, and in fact is C2 in 2 dimensions. And if n equal 2, you even get that u is C2, but let's say this, in particular you have C11. And you can also say, but this is not too difficult to show, that this is like you are minimizing the Laplace square with the constraint that u is greater than f. So that's your energy. So it's relatively simpler than that energy there, but still it's second order energy. And then also the second result, we should just show by using the fact that you can do perturbation on the obstacle only up and not down. So you get a restriction in deriving your Euler-Lagrange equation. You get that the B Laplace of u is a measure. It's a measure concentrated on the, how do you say, it's a measure with supported, let's say, equal mu. It's a positive radon measure supported on the contact set, because outside you have the Euler-Lagrange equation. So the same result can be proved. In fact, the same result we extended with the Japanese collaborator. We extended this result here. I say the same result, it goes the same in the parabolic case. We could not really have the same result in the parabolic case, but I think it's because we had some technical issue to fix. We have a restriction on the dimension for the C11 regularity. But in any case, also in the parabolic case, you can reproduce this type of regularity. I guess you could do also in a nonlinear case, but this I'm not so sure. It would be interesting to extend this type of result to the nonlinear, even for functions, to the nonlinear case. Here, less is known on the regularity of the contact set. there is one partial result in the paper by Caffarelli-Friedman, but the regularity of the contact set is, I would say, less understood in this particular case. And as a final, really final, very final comment is that you cannot expect better than that even in 2D, because of course if you try to do, I don't know, try to solve something like that, uxx equals 0 with the obstacle, for example, you fix here 0, here you want to be 1, so I don't know, 1, 2, u of 0 equal u of 2 equals 0, but then you fix you want to be 1. So now easily you see that here you can explicitly solve, you can find these solutions here are polynomials of degree 3, you can match then you have to put extra condition if you want uniqueness here. For example, you can put, I don't know, some extra condition here. I don't know, ux of 0 equal ux of 2 equals 0. These Dirichlet boundary conditions. This fixes the problem. You can solve it, and you see that in fact you have that the third derivative necessarily jumps here. And so you have, in fact, that uxxxx is a delta up to a constant concentrated in the point 1. So in fact, this is really also in one dimension. Is what, but again, all this is for this linear problem, and I don't know how easy it is to pass from this to the nonlinear. And also the geometric, because the geometric is also a little bit worse than the nonlinear if you don't know a priori how smooth you are. That you can write as a graph, for example. You don't know how to make. So I think that would be an interesting direction also to study. Okay, so thank you very much.
Time for questions or remarks?
I have a question about soft obstacle. What are the essential assumptions on this source term, forcing term, you need to obtain these L infinity estimates on the ball?
Okay, so the assumptions are basically two, that the obstacles are sufficiently regular. Let's say you can write locally as Lipschitz graphs the obstacle first. And so in particular, this gives some bound on the derivative in x of g. And second, the derivative in u of g has to be negative. Which you can do if you write, so because the obstacle inside is like plus constant and outside is like minus constant. So if because when you want to write the equation for ut, to bound ut, you pick up the derivative of g in u, and that if you don't have a sign there, is difficult to. There are some conditions, so Lipschitz obstacle and g decreasing in u, but you can do in this case, and so then you can get the estimate, and so essentially you get a weak solution, Lipschitz.
So maybe I've missed it. Do you have an existence result for the Willmore flow with an obstacle?
No. No, I think you can do in 2D. I imagine you could with some. No, it's just a way to. It was an idea. I think that this method, at least in 2D, probably can be implemented to get the existence of weak solutions. In higher dimensions, more complicated. But however, you still have a problem. For example, as I said, there are these ghost lines. Ghost lines means you have to exit the set work, and then there's this strange variable stuff. So for short time, you expect that you don't have this problem. You would expect you don't have for short times, and that would be already something to prove. And for longer times, you have them, and so the setting is more complicated because this method the energy is decreasing, so you cannot really get rid of those.
So what kind of notion of solution would you then use?
Well, I don't know. I didn't think enough about this. I think just that the method could be applied, but it didn't really work.
It'd be natural to consider a curve written as a graph. You took the obstacle problem for the Willmore energy, and I guess that must be, you'd expect, under appropriate assumptions on boundary conditions, you'd expect to get a local.
I think that
result. Yeah. And that would be the first example for n equals 2, wouldn't it?
Yeah, no, in 2 dimension, of course, you could look at this equation here in one
Oh,
dimension.
no, I'm
for
thinking of
graph.
Wilmore. I mean,
Yeah. You put Wilmore. Yeah.
Think of just think of the Wilmore energy
Yeah. Yeah.
curve.
Yeah. Yeah.
Write it as a graph and look at the obstacle problem
Yeah.
in 1 dimension.
Yeah.
That in itself will have some technical difficulties.
Yes.
But
yes.
then
And you expect
the
C11.
next thing would be giving the program. The next thing you would do it in 2 dimensions.
Yes. Yes. In fact, that.
Graph.
Yeah. What I want to say that one step would be to pass to nonlinear is to go to this formulation. I think that could be done. In 2 dimension, also probably you could automatically have that even in the geometric case you are locally a graph, because to have a boundary energy is already enough to be able to write. So if you can do this in 1 dimension, you probably can do also the geometric case for short time, because the energy it's already very strong for curves. Yeah.
So if you have one of these evolutions with an obstacle, then eventually your surface of your touches the obstacle.
Yes.
How does it do it?
Now, for the mean curvature flow, it will touch the obstacle and it will stay for some time, for some short time, C11. The C11 depends only on the initial data and not how close you are to the obstacle. So it will stay C11. And then at some point you can create, of course, other singularities due to the fact that mean curvature flow creates singularities even without obstacles.
Yeah, but one of the questions with touching obstacles is that if it is spreading along the obstacle surface, it will have or not have a contact angle.
No, because this the regularity is C11 and you don't have contact angle in the sense that it's
When
zero.
you create a singularity, is this because it may?
No, you create singularity basically because in the mean curvature flow it's not due to the obstacle, in fact. It's only due to the fact that you can have thin tubes which shrink. And you do not create an angle essentially because in my energy before I'm putting the wall perimeter and here I'm putting the wall Wilmore energy. Of course, if you change this, it will change the behavior. But with my energy, with the full perimeter, you just touch the smooth. So C11 is the general regularity you would expect, at least for short time, for at least both energies.
So on that kind of question, suppose we had a sphere, that's the obstacle, then we take a plane and we're going to push it up, forcing it, and then the plane, and then we allow the, let's just say it's motion by mean curvature. So then it hits the obstacle, and it begins to wrap itself around the obstacle, but you keep on pushing upwards. So then one of the things you have to deal with, I guess, in a notional solution is when this surface now wants to detach from the obstacle.
Mm-hmm.
The question is do you count the surface which is left behind on the obstacle? It's probably part of, I mean, it's
No, here we do. Here I don't count.
Sorry?
Here with this I don't count because you touch, but then when you detach, you just the perimeter of what stays down.
You've lost, so you will lose area in this instance.
Yeah, well, yeah.
So I mean,
I don't know.
This is the thing.
You look.
Of exercise being what I've been thinking about trying to compute these things. These kind of issues.
I don't know if you lose real, but I don't know this because you touch and that you will have a flat part, C11 solution.
Counted as area tube.
Sorry?
Otherwise, you don't get a C11 regularity.
No, I mean, I'm saying
so that part is, contact is imposed through the conditions. But still, you need to count that part as your area.
You can imagine the moving boundary problem is that the surface is to count the area as on the obstacle.
Yeah, sure.
Now consider keep on pushing up, and it detaches, so you've left behind.
Then eventually you're gonna have a singularity. Then you have a topological change.
Yes, and the surface continues to move up, but you've left behind some surface on the obstacle. So this the definition of solution. If you want to consider minimizing area, you have to take that into account. You have to take that possibility into
You do
account.
that time for at each step of time, and that means that at that time you're counting in,
Yeah.
but not later on.
I'm saying that there are different ways of thinking about the evolution, because you could imagine also not counting the area on the obstacle,
You have two
and
parts.
still have a zero contact angle, right? Away from the obstacle, you're solving motion by mean curvature. You've got contact on this line on the obstacle, but you don't necessarily have to count. You don't have to count the area, right? Do you count the area or not count?
Yeah, well, but you end up with the same solution, whether you count.
Not if you move up.
Yeah, because that is a fixed number.
Not
So
if you leave.
let's go with the last question.
In the minimal surface case with obstacle, in the steady state,
Yeah, but the
leakage
thing is,
obstacles
you need
are
to
enough.
count the area.
Is it also true for the evolutionary case, just with leakage obstacles?
I know.
Yes, well, with Lipschitz obstacle, you just get a Lipschitz with weak solution. Yeah.
But in the evolutionary case as well?
Yes, for short times at least, because again, you can create this type of singularities. But so, for example, if it's a graph, if you're in a graph formulation, you get a Lipschitz solution, and in the geometric case, for short time, you get a Lipschitz sort of weak solution, which is, for example, a viscosity solution or a variational solution. So it's enough to have Lipschitz obstacles to get, but you get less regularity. But of course, Lipschitz in general and smooth if you are far from the obstacles, because there you are just mean curvature flow. Yes, for short time. Yes.
Okay, let's go for the last one.
In this example for linearized Wilmer flow you've drawn.
This one.
Yes, no, on the left. At the contact point, the second derivative is 0, no matter what the obstacle, right? Or no?
No, the second derivative, no, is not 0. Here I'm just putting some boundary condition, I don't care. Now here the second derivative just continues, but non-zero, and the third derivative here will jump.
So it okay, so it can like it does contact with this obstacle at more than one point.
No, well, it depends on the curvature of the obstacle. If the obstacle is very curved, more than the second derivative of this sort of elastica, it's stationary here, for example. If it's very curved, it will touch only here.
This problem.
If it's a thick obstacle, it will be different, because if it's very thick, you will have something like, I guess, something like that. So you touch maybe here and here if it's too. But in general, I guess typically you touch generically, I don't know, in isolated points. So I would say that one can say something more probably here on how is the measure here. For example, in 1D you expect to have deltas generically. I don't know, but I don't know very well. But in the examples you can do, you expect that the measure are typically delta, and the contact set is just points in 1D, of course.
Okay, I think with that we can end the discussions, and we're planning for a picture, so let me come back to that, and thank you.